1.1 real numbers. We're going to start today talking about the real number system. We're going to start actually with a diagram. You may have seen a diagram like this before. You may not have, and that's okay. But for those of you who are more visual than others, I think it can help to see it this way presented. And so we're going to take a look at our real number system from a diagram perspective. The tiny little box in the middle of the diagram are your natural numbers. Natural numbers are the numbers you naturally, or first, start counting with as a child. So if you ask my 7-year-old to count, she's going to start with the number 1, right? And she's going to go up from that until she gets tired of talking, which might take a while. She likes to talk. But that's the natural numbers. Sometimes you'll hear them called the counting numbers. So when we first started in elementary school, you start with this set of numbers, and very quickly you find that you have a need for the number 0, which is not in this list. So we sort of expand our universe just a tiniest little bit so that we take those numbers and then we also include the number 0 in it. And when we do that, those are called whole numbers. So this whole numbers box that I've written, it includes all the natural numbers. So all those numbers that we just wrote are natural numbers and they're whole numbers both, okay? But we also now include the number 0. So if you think about it, we're actually starting with the same list, but we're starting sort of one number earlier in our, ordering of numbers, starting at 0. So as far as like what we operate on, like we add, we multiply, we subtract, all that stuff, that set of numbers works for a really long time in elementary school. And somewhere in 5th or 6th grade, you find that there's a need for a new type of number that are negatives. And so people want you to do something where it's subtraction, but it's subtraction like 3 minus 5. And so we have the integers introduced. So the integers, again, are all the numbers I've listed so far. They include the 1, 2, 3. They include the 0, 1, 2, 3. They include all of that, but they also include what we call the additive inverses, the opposites, the negatives. So if you're writing them in some sort of way, kind of like we already have been, you can kind of write them like this. So this is sort of like a nesting dolls sense, right? We're getting a bigger universe of our numbers as we go. Now, the reality is often before we hit integers, in fact, right now in curriculum, it's usually somewhere in like 2nd grade, sometimes a little bit in 1st grade. Kids actually hit another type of number too, and that type of a number includes fractions. That's usually the type of number they start with, and they see it from a picture point of view, right? Like they have, a pie, and there's one piece out of the 3 shaded in, and they talk about the number 1/3 and so forth. So those types of numbers, including the ones we've already talked about too, are called rational numbers. So rational numbers are those fractions and decimals. And the reason they're called rational numbers is not because they make sense. That's not the hint. The root word here. The root word of rational is ratio for the premise of what we're talking about. And a ratio means that we've got a fraction. So that's where that word is coming from. It's from the word ratio. Just for a reference point, because you'll see it later on anyway, though not frequently used in what we do, there are abbreviations for these number systems. For example, the natural number system is often abbreviated with a capital. I don't really have any space in here. Let me make it just a little bit smaller. With a capital N, sometimes with 2 lines on the left, or it's bolded on the left for natural. You see whole numbers with a capital W. So you got this capital W with either the bolded side of the W or it's double lined. If you're writing it, it's easier to double line than to bold things to make them stand out. Integers are actually not written with I, so you might have been led to think, well, we're just using the first letter. They're actually Z, and it comes from the Latin word for integers, which I should probably look up at some point, but it's a Z. And rational numbers are not an R either. They're actually a Q. And you might be thinking, well, now where did Q come from? It's not Latin. Q comes from the word quotient. Quotient is the same as the ratio idea, right? They're actually a fraction or a division quantity. The reason that we need the rational numbers not to be r, though, is because the real numbers themselves are r. So we can't have the same letter meaning different things. On the other side of this diagram, we have what are called irrational numbers. There's actually not a commonly accepted letter form for irrational numbers. Some books will say I, some will sort of look like it's the real numbers and then take out the rationals, and so there's some different looks for that one. So I'm not going to write anything down, but irrational numbers come somewhere along the way when you start taking square roots. So you might see it when you first deal with square roots like square root 2, right? Because it doesn't have a closed way of writing it out completely. It's this decimal that neither terminates nor repeats. Or you might see it, if you haven't seen it in radical form before, then you might see it when you are encountering about 7th grade pi, stuff with geometry and calculating like circumference and things like that. And then you've definitely seen it when you get to high school in either one of those two fashions, but then sometimes, depending on what your high school experience looked like, you might have also seen the number e. And that sometimes hits in about Algebra 2 or a pre-calc class or something like that. We won't get too far into the irrationals. We'll do a little bit with them this year, but not a whole bunch, and not with great depth. You'll see most of those in college algebra, but they are there. So this first chapter, or verse section of this chapter on real numbers, encompasses a lot of different things, so it's going to feel like it's a little bit disconnected. I'm sorry for that, but we just need to set some groundwork. And so the next topic we're going to look at is number line graphing. So one thing to remember is it's like we read English. Not all languages actually read the way English reads, but in English we read from left to right. So we start on the left, and it's going from left to right, which means we use our smaller values to the left of our bigger values on the right. So when you see a question asking like this one to graph 2.3 on the number line, you might be tempted to do lots of things, but at the very least you need to have 0 put on there. I mean, that's a reference point for us, and you need to figure out where 0 would be after that. So you might mark 1, 2, 3, and then somewhere in between 2 and 3 would be 2.3. So sometimes in your homework it'll already give you a graph, like a grid, and so you have sort of an advantage of not having to draw it yourself. But if you are drawing it yourself, you need some reference points, those big hash marks being my integers, right? So this is 1, 2, and 3. And then the number that I'm identifying, I'll shift it up here, is 2.3. I have an image here that says, what is the actual location of A? So I'm going to draw you an image that might show up like on a homework, so you can kind of see what you might be expected to look at and determine. So start on your number line as you're drawing with me what would be on the paper to start with, and start by saying 2.2. And then .3. So there's all these hash marks. There's 10 of them, right? There's 9 hash marks between 2.2 and 2.3. And the point that it identifies is this one. And you're supposed to figure out what that value is. So whatever you write down has to be between 2.2 and 2.3, right? So if you think about this, it might help to have a reference point of money. 2.2 is kind of like $2.20. So if it helps you, you could put a 0 after that. And the 2.3 is $2.30. So all of these values in between are representing like the penny counts up, right? So maybe you can see it well enough from where you are. I kind of hope so, but can you tell where that red dot is? What's it at? Yeah, it's 2.26, you're right. So it's a lot easier when it's already printed out for you on your paper, I get that, but this one's 2.26. So if you're looking for pieces between them, make sure you are in fact giving answers that are between the values. Feel free to add zeros on the end if it helps to give you sort of a reference point, because obviously if you're only considering the 10th place, right, the 2 here and the 3, there's no space in between them until I have a second digit I'm considering. So keep that in mind. All right, let's look at inequalities. Any questions about number line stuff at the moment? So you got to go both directions, be able to place it on the number line and be able to read it from a number line. All right, inequalities is next. There's actually 5 inequalities. They're not all used equally so. I mean, we don't use all of them that much. But there are 5 different inequality notations. So these symbols each have a meaning. The first one is less than. So sometimes people like to equate that to looking like it's sort of like a leaned over L, right? To remind themselves that that's less than. I'm going to go across over here, and this one is very similar, but it's less than or equal to, because it has that line underneath. The next one is greater than. So the corresponding one on the other column is greater than or equal to. And those 4 are kind of used a lot. I mean, like if you see an inequality, it's probably going to be one of those 4. But by definition, the last one actually is an inequality. What is this symbol? It's not equal to, which is exactly what an inequality means. It means 2 things are not equal. So by definition, it falls in this category, though we don't see it used very often. And the kinds of questions that you're going to see are going to be framed like this, where you're simply deciding which of the 2 values is bigger or smaller. So again, decimals are kind of nice because we have money as a reference if it has 2 decimal points or less, 2 decimal points or fewer, so that's nice. So as we're looking at 6.21 and we're looking at 6.13, which one's larger? Yeah, the 6.21 is larger, right? Like that's like 21 cents compared to 13 cents if you're thinking in terms of money. So this one's larger. So the direction of the inequality will always open toward the larger value. So that would be the 6.21 like this. So we have 2 options of answers that can go in this blank, and they're both correct. If you put this in the blank, you are correct, right? 6.21 is greater than 6.13. You are. But you would be equally correct if you put greater than or equal to. It doesn't mean it is equal to. It just means it's an option. But it's not wrong. It is greater than or equal to. It's the greater than part. But either of those answers in that blank are equally correct. So there's a little bit of flexibility as you're answering those questions, and you can sometimes have multiple answers and they'd be correct. Any questions on inequalities? We will get lots more into inequalities later. Right now we're just comparing digits of numbers. That's it. Okay. So I already mentioned a little bit about square roots. We're going to encounter square roots in a couple of fashions in this section. The first one, a square root is one of 2 equal factors of a number. That's the definition. Principal square roots are the positive, I'm sorry, I shouldn't say positive, but non-negative, it's written here, non-negative square root of a number. So let me give you an example about the number 64. If I just said, find the square root, I'll abbreviate, of 64. If you just had that written out in those words. There's actually 2 answers. One answer is 8, right? Because 8 times 8 is 64. What's the other answer? Some of you are mouthing it. Negative 8. Because what is negative 8 times negative 8? 64. So it's not real helpful a lot of times in mathematics when we arrive at operations that give us 2 answers. I want to make sure that I'm getting the answer that's useful for the context I'm working in. So the context, when you see a radical, is that the radical is always asking you for the non-negative answer. It's called a principal square root. So it's actually correct to simply say that the square root of 64, as it's written here, is simply 8. And in fact, it's incorrect to say it's 8 and negative 8. Because once you see that notation, that radical notation, right, that square root, it's saying to you, I only want the positive. I don't want any negative numbers coming out of this. That's what it's telling you. So we all end up with the same answer when we get to that particular question, phrased that way. Okay, Make sense so far? Okay. So every time I teach this next part confuses people. So at least the example I'm going to do. There are numbers that are perfect square roots, right? 64 is an example. I just look at 64 and it has a nice whole number solution, a nice rational solution. It's 8. So a number with a square root that is a rational number is a perfect square root. But not all values have that property. So for example, right, 64 is a perfect square root. What's another number you know that's a perfect square? 81. What else? What was it? 25. You got it. Yeah. 36. We even have like the number 4 and 9, right? Yeah, so these are values where when we take the square root, and these especially, we get out whole numbers. I mean, they're really nice. Technically, we could actually look at things like even like 9 over 4. Because the square root of the top is perfect, the square root of the bottom is perfect. So it's also a perfect number. It just ends up giving me a fraction as an answer. But it's easy to do. It's not giving me something that's irrational. Now it's back on. Okay. But there's lots of examples of things that are not perfect square roots. In fact, there's a lot of examples. So can somebody give me an example of something that's not a perfect square root? 1 actually is, because the square root of 1's 1. Yeah. 12. Okay. What else? 3. About 26. We could go on all day. Actually, in both of these lists, we could probably go on for all day if we wanted. And making lists of things, that would be not a good use of our time. But there's lots of numbers that are not perfect square roots. So what our next question is actually asking us is to sort of think about square roots in sort of a sense of like if I put them all in order. So if I think about my perfect squares and I were to put them in order, I'm going to take these numbers out for a second and kind of look at them in a different way. If we started with the 1 that you mentioned as our first one, because 1 is the same as 1 squared, and then we could do 4. It's the next one because it's 2 squared. So after 2 squared would come 3 squared, which is 9, and then 4 squared, which is 16, and then 5 squared, which is 25, and 6 squared, which is 36. So we actually kind of have a way of writing them out in an orderly fashion too. If you think about it from an orderly fashion perspective, it might help you to understand what's going on in this next question. This next question is asking you not to give the exact value of the square root of 20. Nor is it asking you to grab your calculator, plug in square root of 20, and tell me what's before it and after it, which is what people usually do when they get here and they're like, I'm not sure what to do. Calculator. It's not what it's asking you for. It's asking you to think about where 20 lies on this list of numbers. What 2 numbers does 20 lie between? 16 and 25, right? So if we're thinking about this list of numbers, we're right inside between those two. So we've got 16, we've got 20, and 25. Okay, because we're sandwiching it between the 2 that it's most near on either side. So when the question asks you to find consecutive whole numbers that it's between, we can do that because we can actually find the square root of each of these. What's the square root of 16? 4. And what's the square root of 25? 5. So it means that the square root of 20 is between 4 and 5. That's all it's asking you for. So if you want to make a list, you can do that. If you want to have a calculator there to keep going, like if the number were bigger, like let's say they gave you 111. And you're like, oh, well, that's kind of further along my list than I wrote down. Well, you could actually at your calculator do that, right? It can go 3 squared, 4 squared, 5 squared, 6 squared. It can get to the point where you're right before and you're right after, and those are the numbers you're looking for. Now, on this one in particular, this is the kind of work I'm looking for in this particular problem. For you to identify the squares, the perfect squares that are around them, and to show that it's between those perfect squared numbers, the 4 and the 5. That's what I'm looking for. Okay? Any questions so far? All right.